because now we took actually a big step before. I just showed you how to do statistics for in an exponential distribution situation. No basic stats classes around the world. That's pushing it. Few. You will find that. Of course, more and more are realizing that we need to go computer-based, but it's not at all. It takes a long time to change. There are thousands and thousands of introductory statistics textbooks. I get them in my desk every month, basically, people trying to sell their textbooks. And we don't want to buy them anymore. We did our own. It's much better. And you will help us making it even better. And we have this whole R simulation thing built into it. It's so nice. Here's another big step for you, way beyond what you would usually get taught by explicit small formulas in a stats class. Let me show you how we can do not only having a distribution which is not the normal, but let's compute something completely different than the mean. Something actually pretty nonlinear, actually, if you think about it. The median is simple to compute, but as a formula, as a function of all the x's, it's actually a pretty complicated nonlinear function. It's not something where you can apply mean and variance rules very easily. If I know the mean of something, I cannot just apply it inside, outside. It's a nonlinear function. It's pretty complicated. How do I do it, you think? How could I find a confidence interval? Again, of course, I can compute the median easily. I taught you that back in chapter 2. It would be 21. I could also compute the mean. I'm going to use both of them, actually, for the procedure. I didn't teach you how to do such things. But I think already now you may easily... I'm going to show you a number of these R things now. I'm going to show you a number of method boxes that try to formalize what I do. All of them are more or less the same thing, right? And I've already shown you a couple of them. There are a number of different method boxes, but it's essentially the same procedure in all of them, right? Here it comes again. Number of simulations, set the seed. This is the same thing, exactly the same thing as before. 100,000 times I have 10 exponentials now with the right mean, the mean coming from the data, such that the exponential is the best possible exponential to match the data I have. That's the one I should use for this. And then I change one little thing. I am so lucky that there is a function in R. There was a function called mean that I could use. There is also a function already in R called median. You have seen it already. I can just compute the median each of those 100,000 times and then see how does the median behave from time to time. Same idea. I think I brought the histogram again. Here's the histogram of all my 100,000 medians. I didn't make the point before, but let me make it now, just as before. I can see this distribution. It's pretty skewed, right? The sampling distribution of the median of exponential distributions, 10 of them, is definitely not a t-distribution nor a normal distribution. It's not a symmetric distribution. So using procedures based on t or normals would be wrong. How wrong is a question of investigation, of course, but definitely wrong. So I just do the naive, straightforward thing. Let me read off the quantiles from those 100,000 numbers that I just showed in the histogram. Here's the 2.5% and this 97.5%. The confidence interval is 7 up to 38.4. Easy, right? And I've done something complicated. Confidence interval for the median of exponentials. If I asked you to do the theoretical derivation, how this method should be done based on math, you would need at least 2 or 3 classes. And maybe those classes for you, for some of you it's nice to take those classes to move on and be experts in this field. We need more experts in stats, I assure you, and stats and data analysis. it's a competence that is lacking in the companies out there. So if you want 100% guarantee of a nice job here or New York or Silicon Valley, wherever you want to go for that. Hey, but if you don't like that, if you want to go for your own engineering field, fine with me. You do that. But then again, maybe your effort is better spent taking 3 classes in your engineering field than spending 3 classes on probability and math to learn how to find a sampling distribution for the median of an exponential. But hey, you may be hit by needing to do statistics for the median for an exponential when you get in your own engineering career out there, or something much more complicated than that, probably, most likely. The real life that will hit you is much more complicated than the median of 10 exponentials. I'm sorry, it is. Here is the general procedure covering both of these 2 things that I have shown you after the break. The parametric bootstrap procedure for what as I say, to find the confidence interval for any kind of feature that I might compute. I call it theta. It's just to emphasize that it could be the mean, it could be mu, as I was used to before the break. It could be the median, it could be the it could be anything that I would like to compute based on these numbers. I call it theta, right? Anything. It includes both the mean and median things that I've shown you. One method box that will include both of these things. And it's pretty boring, but I'll show you 4 of these before we are finished now. 4 of these will pop up, and they're almost the same. If you think, why don't you just make 1 then? Well, then last year I had 8, so I'm improving. Anyway, I think it's nice to have 4, and if they're the same, you can get used to looking at them, so you don't have to read all of them word by word. How do I find how do I formalize in what I've just done? Well, I simulate 100,000 times. I simulate 10, because that was my specific situation, that I had 10 in my sample. From the assumed distribution in my example, it was the exponential. It could be anything else. Here's a little thing. That's why there is a big footnote here. Which in the HTML version, if you read it on screen, it doesn't appear very nice. We know that. It's going to be fixed by next year, but for now it's as it is. In the PDF, it looks nice. I have to plug in, for instance, as we saw in the exponential, to use this procedure, I need to compute the mean and use the exponential with the computed mean. That's what I'm talking about here. How do I actually do it in practice? Even though I say exponential, I need to know which exponential. Now, if I am going for a normal or a log normal thing here, it becomes slightly more complicated, because the log normal and the normal not only has a mean, it also has a variance, right? So there are 2 things that I need to know the value of to be able to simulate from the normal or the log normal. Hey, but then all of these words in the footnote says, just compute the variance then. If I need a variance in the normal, compute it. Now the footnote is preparing us for a little more generality than that. It also says, what if I, in my future engineering career, meet a new distribution with maybe 3 unknowns, not only a mean and a variance, but something like a curvature, what's called skewness factor, or a steepness factor. There are many other distributions where we need more than 2 unknowns, right? Engineering practice also means distributions with more than 2 unknowns, not only the mean and variance. Well, then I can reassure you that we know how to deal with it. There is a general principle for how to match data to distributions, or rather, I should say, distributions to data, such that if I have unknowns in the distributions, I will always know how to extract the unknowns from the data, like computing the mean and the variance, right? It can be done by general principle of maximum likelihood. I have some extra math videos on that principle. We don't really need it in our course, but basically all we do is actually maximum likelihood, which is a general principle for doing stats, actually. So it's one of those things. The big one, he's out there taking care of us, but we don't need to think of him every day. At least some of us practice it that way. Right? Sorry for... Oh, my God. Let's move on rapidly. We simulate. We calculate many times whatever we need to calculate. The mean or the median or whatever, right? I call it theta hat. Whatever I'm doing statistics on, I calculate it many times. And at the end, I look at the quantiles. I look at the quantiles. That's the 3 points. I've done it a few times. Put into formal procedural math language. Simulate, calculate, look at the quantiles. And in R, it's almost just 1 or 2, 3 steps, right? One more example, making a little point within the same, for this, covered by the same method box. And as you will see on the time, some of the last method boxes for today will be much more rapidly shown to you, but they are basically the same, so don't worry. Let me show you something. What if I would like to make a 99% confidence interval for the upper quartile? Just to throw you something completely new in your faces that I haven't even talked about before. How the heck could we even think about doing that? It's very complicated mathematically. But still, actually, now I'm not complicating the thing about the distribution. Let me just stick to my normal distribution, as I've been used to before the break. I'm showing it to you because I'm having the challenge now that in my apply function, where I'd like to do the computation, the theta computation, the theta hat computation, theta is now Q3. There is not a function in R called Q3. There was a function in R called mean. There was a function in R called median, but there is not a function in R called Q3. It's not that we cannot compute Q3 by R, but it's not an explicit function of itself in its own right. And we need that to repeat the R technical way of doing it. So, to take this beyond functions that exist by themselves in R, functions that pop up as the relevant ones to us, we need this little extension of R, being able to use R. We need to be able to specify our own R functions. And it's not extremely complicated, as I hope you can see here. If I know how to compute Q3 in R. This is the way I've taught you already back in chapter 2, how to compute Q3 in R. I should use the quantile function in R, which is there. And I should plug in the Q3 percentage, which is 0.75. Then I get the QR as an output, so I can compute it. Well, then I just make a function of my own, specifying that the output of the quantile with 0.75 should be the output of my function. I hope you can follow me. I'm being split. For some of you, you're almost, it's really like embarrassing, I know, as explicit I am here. This is a point where you are very diverse. I have to tell those of you who think it's ridiculously easy for you now, it's not for every one of you. You are very diverse in your, that is my experience at least. If you prove me wrong, I'm happy. Hopefully, happy, not the opposite. Some people challenge with this. For other people that are used to IT, it's a piece of cake, of course. It's not a thing. If we define our own Q3 function, we just redo everything I just showed you, and then I use my own Q3 down here, and then everything goes as before. Simulate, compute the Q3s, look at the quantiles. 1, 2, 3. Tick, 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 from before, right? We jump to the next one. The last